Good morning, everyone. This is in continuation with the concepts that I explained to you about thermal stresses in the previous class. So we know that any body which is applied with a load like this, P, which is held here, so you'll have a stress which is actually P by A. So that is actually by applying an external load. Now, can you actually have loads or stresses built up in the material when there is no external load applied? It can happen due to increase in temperature. We'll be explaining it how now. Okay, first of all, we need to understand what is actually thermal expansion. So thermal expansion, so if I let me get some place here. So thermal expansion. So thermal expansion TE is proportional to the original length of the body. Suppose if it is a body here, and now if it is the original length, and if you try to increase its temperature by delta T, then it will expand. So definitely you can see that it is proportional to increase in temperature. And also if you got longer length, it will expand more. So it is also proportional to the original length. And then this thermal expansion, this proportionality sign can be removed, and there can be one proportionality constant here, which is multiplied both with delta T and L. That proportionality symbol is also alpha, and which is called as coefficient of thermal expansion. Coefficient of thermal expansion. And few example values of coefficient of thermal expansion for steel is 12 into 10 to the power of minus 6 per degree centigrade. Per degree centigrade, which we actually have to repeat in mind. This is meter per meter degree centigrade. And for copper it is how much? 17.4 or 18 around. So 17 into 10 to the power of minus 6 meter per meter degree centigrade. And for aluminium it is the highest, which is actually 12 into same thing. Okay, so these are actually the thermal coefficients of expansion. Now if you know this, then you can easily find the expansion. So this thermal expansion, basically you can call it as DLT, which refers to extension due to increase in temperature. So DLT, so sorry. This is actually 24. Steel is 12, copper is 17. Aluminum has got almost double the expansion when compared to steel. For the same 1 meter length of the rod, for every 1 degree centigrade in rise in temperature, it will expand by 12 into 10 to the power of minus 6 meters, or you can say 12 into 10 to the power of minus 3 millimeters. Okay, so this is it, and therefore using this formula, okay, I think this you cannot remember this formula. So this DLT, increase in length or decrease in length. Of course, if you increase the temperature, it will expand. If you decrease the temperature, then it will get contracted or reduce its length. So both can lead to stresses in the material. So we'll see how now. So increase in length or decrease in length can be given by the formula alpha into delta T into L. Now we'll try to see how we can actually find out the thermal stresses using this formula. So you understood this concept now? Okay. Now we know that Now this body, now which was of this size, imagine this body is like this. Now you are trying to hit this body. Maybe you have a flame here, maybe you have a flame here, and you are trying to hit this body. Now this body would expand, and so much it expands can be given by this formula. dl T is coefficient of expansion 12 into 10 to the power of minus 6 for steel, multiplied by increase in temperature multiplied by the original length will give you increase in length. Suppose if you allow the body to increase its length, then there is no stress built up. Suppose if you block this body from expanding, then the body wants to expand, but it is not allowed to expand. Then you see the stresses start building up into the body. So suppose if it was allowed to expand, that was called as free expansion. So free expansion, suppose if it was allowed to expand, it will expand by this much, which you call it as free expansion. That is given by alpha into delta T into L, which is actually dl, change in length due to temperature. So this amount of deformation which would be caused by application of force, that has to be equated to this. So what I do is I equate this to the formula that we have already used here. So we know that for any body which is applied with a load P, change in length is given by the formula PL by AE. Now this P by A can be written as sigma, and this as L by E. Okay. Now this, if you are not allowing this to expand, suppose if you are not allowing this to expand, then the amount of stress which is built up in this is given by sigma for the same dl for which it is not allowed to expand. So you should equate this equation and this equation. So now if you call this as equation 2, if you are calling this as equation 1, equating 1 and 2, equating 1 equal to 2, so you got alpha into delta T into L, which is equal to sigma, or otherwise you can actually equate 2 and 1. You can write that equation first. So this equation first, sigma L by E equal to alpha into delta T by L. So then you are left with, so L and L cancels here, and what you are left with is sigma is equal to alpha into delta T into E. So you don't have to remember this equation, you just have to remember that you need to equate this restricted expansion. So basically you need to understand here, sometimes you may have a rod here like this. You may have a rod here like this, and here there is a wall. Hello. You need to understand this concept of free expansion and restricted expansion. Imagine that this gap here is 1 mm. Imagine that this gap here is equal to 1 mm. Suppose you heat this body in such a way that this expansion is equal to 2 mm. Now this expansion is equal to 2 mm. So that means without this restriction, the free expansion is equal to 2 mm. So that means without this top, without this wall here, the body would have expanded by 2 mm. The body would have, this rod would have expanded by 2 mm. But there is a wall at a distance of 1 mm. So out of 2 mm of expansion, 1 mm we call it as free expansion. So free expansion, and this we call it as restricted expansion. So let us not worry about the word free expansion here, because people confuse. They would say that suppose if it is allowed to expand, it will expand by 2 mm. That's called the free expansion. So you can say that this gap, suppose if you call this as gap, suppose if you call this as a gap, then this free expansion, now this restricted expansion is equal to free expansion minus gap. So free expansion means if it was allowed to expand, it would have expanded by 2 mm. So minus the gap, that will give you restricted expansion. So that means the body is restricted to expand by 1 mm. That value of 1 mm has to be substituted here, where in this equation. So don't worry about this. So you have to first substitute this value here and then find out the thermal stresses. So we'll show you how it could be used to find this value here. So this value, this whole value is called as the restricted expansion. This will give you a restricted expansion.